And start this. All right, so we're going to actually start our periodic table notes. First set of notes, so everybody should have them. Let me know if I'm going too fast or too slow. Some of this should be familiar as we get going. Hold on. And again, bear with me with my new technology too, because that's not exactly worked out all the kinks either. So, do ideas and theories stay the same? I see some head shaking. No. Things are always changing, right? So science is definitely the same. So all around us, things are changing. As new ideas come around, we have to be able to adapt. We talked about adaptation last year in 8th grade. It is massively important not to be rigid and stiff in our ideas and our beliefs. So here's an embarrassing example, and I don't know if I used this last year or not. When I was doing my student teaching, I was in like a 4th or 5th grade classroom was one of my placements. And so I go in there and they were talking about the solar system and they kept saying 8 planets. And I'm like, 8? There's 9. Like, I learned that there were 9. I didn't hear that we had lost one. And so the whole time I'm like, oh my gosh, that's not right. Like, all these students, the teacher, everybody believes that there's only 8. What am I missing? So I went home that night and I started looking it up. Well, sure enough, Pluto became a dwarf planet. It is not technically a planet. It doesn't meet all 3 requirements to be considered its own unique planet. So I had to adjust my thinking. I didn't just go in there and stomp my feet and be like, there's 8? No, there's 9. I know there's 9, right? I had to adapt. I couldn't just be like stuck in my old ways, like, there's 9, you guys are dumb, I'm right. That's not a really good look, is it? So we as humans, we as scientists, we as students, we have to be willing to adapt. Same thing with the explorers. They used to think that the Earth was flat, right?
There's still flat earthers, and it drives me crazy.
There are a few random people like Kyrie Irving who believe that the Earth is flat, or maybe he's been educated now. But back in the day, we didn't have all of the information that we now have to help guide us. And so they thought that if you just went sailing, at some point you're going to fall off like a waterfall, right? You get to the edge, you go down. Didn't realize that the Earth was round, didn't understand gravity. We didn't have all that information, or they didn't have all that information available to them. So as they started sailing and these explorers started going, think how, I don't know, maybe brave or crazy or both they were, thinking, I'm going to sign up for this trip, knowing at some point I'm going to reach the edge and we are going to probably either fall off or we're going to have to try to backtrack. But obviously that didn't happen. They were able to sail all the way around and return, realizing, oh my gosh, the Earth is round, it is not flat. So not only do scientists have to change their thinking, but humans in general, right? So there's just a few examples of us having to change and alter our ideas. So we're continually adapting, making room for that new information. And if something doesn't seem right on the notes or I'm going too fast, let me know. And so this is most definitely true of the atom. And that's where our unit starts, is with the atom. No one has ever seen an atom. Just like the Bill Nye showed, it is so small that it reaches the smallest particles that cannot be divided anymore. But we have done a lot of research, we have a lot of information, so we do know a lot about it. We've never technically seen a dinosaur either, right? But we know a lot about them. So the same thing is true. Atoms, dinosaurs, we haven't personally up close seen an individual one, but we know that they are there. Okay, sorry about that. Little paperwork. All right, so This is slide number 4, the atom. We know that this is the smallest particle of an element that retains the chemical and physical properties of that element. So when I'm saying elements, if you look at the periodic table over there on the wall, right, all of those little tiles or squares represent a single element, okay? And so right now we have like 94 naturally occurring elements and then 24 that they have kind of simulated under special conditions in the lab, but 94 that are naturally occurring. And the Bill Nye yesterday had a really good example when he was sitting there with his little book reading through the letters. He said that the atoms are like the letters, and you put the letters together to make the words, which are our molecules. And then you put letters and letters together to make words, right? So we're taking atoms plus atoms and making something bigger. So H2O, that's a molecule of water. So it's combining elements in set ratios to make something new. So it's not just hydrogen and it's not just oxygen anymore. It's this brand new thing. So it's not like it's the letter B and the letter E anymore. It's combined to make a new word of BE, right? B. So if you think of it kind of like that, sometimes it helps kind of put all those elements into kind of perspective. And hopefully this kind of looks familiar. This always reminds me of like the Jimmy Neutron little logo. If you guys watched that at all, it might have been a little bit before your time. Did you guys watch Jimmy Neutron?
I've seen like one.
Seen a few, not as popular. Like when my son was younger, Jimmy Neutron was super popular. Lost my mouse again. There we go. Okay. So there are two things about the atom that we can actually measure. And these are going to be the two properties that we're focusing on because they are measurable. It's mass and it's charge. When I say charge, what do you think of?
Electric charge.
Okay, good. And what signs do you normally think of? Don't blurt it out. Give everybody a chance to answer too. What are the two main signs that you think of when you think of charge?
Positive and negative.
Yeah, positive and negative. Very good. All right, so mass, like how much of that object or that atom do we have? And then charge, is it positively charged or is it negatively charged? And so that charge is really dealing with an uneven number of protons and electrons, because I will tell you, 100% of you got right that the proton is a positive charge on the pre-assessment yesterday. So that was awesome, like great place to start. So you have some things that are going to be positively charged because they have more protons, some things that are going to be negatively charged because they have more electrons, because the electrons are what have the negative charge. And most of you got the negative that went with the electron charge yesterday too. Okay, so the atom. I'm going to look at kind of the setup. Like I said, you guys all knew that the protons were positive and that those are in the nucleus. So the nucleus is kind of like the central location. To me, it's kind of like a beehive. If this is the hive, that's where most of the action is, right in there, right? That's where the majority of the space is taking up. But then buzzing around it, you're going to get the bees. And the bees are kind of like, to me, the electrons. They're around the outside. Right, so the protons are in the middle. With the protons are the neutrons. And we're going to learn here when we get to our nuclear reactions that the neutrons kind of act like the glue to hold that nucleus together or hold that hive together. The neutrons have no charge. Neutral, neutron. And then finally, the electrons. And I said the electrons are what's buzzing around on the outside. They are not fixed and set in the nucleus like these two are. Does that all sound pretty familiar?
Yeah.
Perfect. And that's what those last 6 questions yesterday were pretty much based on, that information. So the electrons are outside. All right, so in the nucleus, This is in the center of the atom, more or less. And it contains the protons and neutrons, just like our picture showed. But it's only occupying a really, 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 really small portion of the entire atom. Okay? Only a really small portion. So yesterday in the Bill Nye, he showed like if he ran 500 meters, if he started, that was like the nucleus. When he got to the 500 meters, that was like the outside edge of the atom, and that's where the electrons would be found. So you have all this big empty space between the nucleus and where you find the electrons. All right, so again, think of like a beehive. The hive is here, and then buzzing around it on the outside, kind of away from the hive, are the bees. Something that's kind of interesting and kind of that you wouldn't necessarily expect is, even though it contains protons and the neutrons, its mass is really, really small. Because it is so tightly packed, it's super dense, tightly packed, but it has a very, very small mass. The protons and neutrons are about 1/10 the size or the mass of a normal electron. So that means when you start putting all these protons and electrons together, or excuse me, protons and neutrons together, that you have almost about 2,000 times greater the mass for one single electron. So in an atom, you're getting a lot more mass coming from the electrons than the mass coming from just what's going on in the nucleus with the protons and neutrons. See why the vocab is so important? I mean, you can't really understand what we're talking about unless you have an understanding of these words: charge, electrons, neutrons, protons, nucleus. All right, so the electrons. They are found orbiting around the outside of the nucleus, and as you get into chemistry, you're going to learn a lot more about these levels, but they call them different energy levels. Sometimes you'll hear them called orbits. Here it kind of looks like you're looking at like a bullseye or a target. Like, so here's the nucleus, and then here you get into your different electron levels. We're keeping it very simple. Physical science is a nice introduction to a lot of things, but the details of them will come later. So if you take chemistry, you'll get into this more. Yes, sir?
That image kind of looks like a solar system.
Yeah, it does, doesn't it? With the blue being like the sun? Yeah, I agree.
And electrons being the planets.
Yeah, that's a great way to think of it. Great way. So atoms can actually gain electrons. They can borrow them or take them, sometimes share them. And that will give the atom a negative charge, because think about it. If an electron is negative and you've just taken some negatives, you make that atom negative. If I block you guys, if I'm standing in your way, just kind of shoo me out of the way. Sometimes I stand in this corner and block your angle. So if you get extra electrons, you've just made the atom negative. If you lose electrons, now you have more positives. You've just made that atom positively charged. So a lot of what we do in here, I'm going to ask you to think logically instead of trying to memorize. Because trying to memorize things, a lot of times, it'll stick with you for a day or two or maybe a little bit, but it doesn't stick with you long term. You think about it logically and can like rationalize what you're looking at, it's easier to keep everything straight. So if you just think about it, gaining negatives, now it's negatively charged. Losing negatives means you have more of your positives, making it positively charged. So again, don't try to memorize that, but just think about it logically. And so we've had a lot of different models of the atom through the ages. And so this is where that adapting and kind of modifying your belief on things definitely is true. So we're going to go through a few of the original models for the atom. We're going to come back to this video. I apologize. Sometimes the videos in here that I normally would play at a certain point, we're going to skip just because I don't want to stop the video or have the video record this video. So we're gonna skip this and come back to it. I will save time at the end, I promise.
Because copyright infringement.
No, not because of copyright, because I said I don't wanna record and have it recording longer than necessary. It takes long enough for things to upload as it is. Okay, so we're gonna look at 3 or 4 different atomic models. So this is called the evolution of the atom. So our understanding and how it's changed over time. So we had 6 pretty important changes. The first one, we give credit to Democritus, and then John Dalton, J.J. Thomson, Ernest Rutherford, Niels Bohr, and finally something called the electron cloud model. This is more for your information, just so you can see that I'm not making things up, that, okay, this is how we learned about the atom. Since we can't see it because it's so small, how did scientists know about this? And so this is just for you to kind of see where this information came from. I'm not going to test you on this, but I think it's important for you to understand where it came from. So, in around 400 BC, Democritus was like a philosopher. He was one of our original great thinkers, and he is the one that proposed that atoms make up everything, or that everything's made of atoms. He thought that atoms looked kind of like a sphere, so in his mind they were this sphere or ball-like shape. And so he also thought that they wouldn't be able to be divided, and like the Bill Nye showed yesterday, the word atom means indivisible, meaning it can't be split. So like when he was trying to cut that cheese, right, and nobody even snickered at cut the cheese. I was kind of impressed with your maturity. But when he cut the cheese and kept cutting it, got down to where he couldn't divide it anymore. And so that's where the name came from. Now, John Dalton kind of went with that idea, and he proposed something called the atomic theory, that atoms cannot be created or destroyed, that elements of the same, or atoms of the same element are exactly alike. This is true. So if I look at the periodic table and all those 94 elements, I could take 100 oxygen elements or atoms and they would all be the exact same. I could take 1,000,000 carbon atoms, and if it has 6 protons, then it's carbon, and they're all going to be the exact same. So the atoms make up your elements, but they have to have certain characteristics, and that's what makes an oxygen different from a carbon, or different from a lithium, or different from a boron. And that's what we'll kind of look into, like what makes these elements different from each other. If they're all made of atoms, what's different about the atoms to make something carbon and something else neon, or to make it selenium? So we'll take a look at that too. Atoms can combine in whole number ratios to form compounds. This is like our molecule, our H2O, taking those individual letters, putting them together to make words, taking our individual atoms, putting them together to make new molecules. So you take 2 hydrogens and 1 oxygen. Now it's not just hydrogen, it's not just oxygen. You put it together and you have this brand new thing of water. Okay. And in chemical reactions, atoms are combined, separated, or rearranged. John Dalton was on the right track. He was really, really pretty, almost perfect in his understanding. Now, J.J. Thomson, he actually took John Dalton's work a little bit farther, and he came up with wanting to test out what would happen if you ran electricity through things. Like, what's it going to do? And he did some experiments using something called cathode rays, and he was able to use these negatively charged particles to kind of see that there's something going on inside the atom, right? So since atoms themselves are neutral, they're not positive and they're not negative, he decided that there has to be something that is positively charged in the atom. And that's the first time anybody really kind of got that specific, to realize if he's putting something negative into it, there's something positive there that's kind of reacting with that. So he came up with this plum pudding model, where the pudding itself is positive goo, and then the negative electrons are kind of like the plums. So plum pudding, it's basically like a raisin pudding. So it's pudding with raisins in it. I know it's probably not something that we have eaten. It's more of a British thing. But if this is the positive pudding, then these electrons are the negative plums, or, you know, they also use the raisins in them. So that was a little bit off, but he was on the right track thinking of there being something positive and something negative. All right, so this was known as the plum pudding model. Okay, this part is not in your notes. You're gonna see that it goes from, you know, you have a big spot where it skips. So we're still not in the notes. Again, this is just for background information. But he discovered that the electrons are in the atom because he was able to run electricity through this tube, and he had gas in the tube. And when he ran the electricity through it, it excited something. And what it was exciting was actually those electrons, and they gave off light. And so this is called a cathode ray. Okay, again, this is just showing kind of what he used to kind of set up his experiment to realize, wow, there is something electrically charged in there. Right? And there is a video here that we'll watch. So if you're looking at this, remember how magnetism and electric currents are related from last year. And so you can see this electric charge is going through, and here they must be oppositely charged. This is negative and that must be positive because they're attracting, right? Those opposites are going to attract. So he's actually bending that current towards the positive side of that magnet. Okay. And so when that current was passed through, they were able to see that those electrons started to glow, right? And then knowing that they're negative, you put that positive end of the magnet, you're going to get that attraction. All right, and so we'll watch that one at the end as well in just a few minutes. Let me see something real quick. Let's go ahead and stop there, I think. I think that should probably be, we'll start with this tomorrow.